Welcome to this coding walkthrough. In this session, we'll be tackling LeetCode problem number 2074, titled Reverse Nodes in Even Length Groups. We'll break down the problem, explore the intuition behind the approaches, and analyze the solution step by step. Let's dive in. The problem asks us to modify a given singly linked list by reversing certain groups of nodes. Specifically, we divide the linked list into groups of increasing size, starting with a group size of 1, then 2, then 3, and so on. However, we only reverse the nodes in a group if the size of that group is even. For example, the first group will always have one node, which is odd, so it won't be reversed. The second group will have two nodes, which is even, so it will be reversed. This process continues for the entire linked list. The goal is to return the modified linked list after performing these operations. The input to the problem is the head of the linked list, where each node contains an integer value and a reference to the next node. The output is the head of the updated linked list after applying the reversal rules. Let's consider an example to understand this better. Suppose the input linked list is 5, 2, 6, 3, 9, 1, 7, 3, 8, 4. We divide the list into groups based on their sizes. The first group has one node, the second group has two nodes, the third group has three nodes, and the fourth group has four nodes. Now, we examine each group to decide whether to reverse it. The first group, 5, has an odd size, so it is not reversed. The second group, 2, 6, has an even size, so it is reversed to 6, 2. The third group, 3, 9, 1, has an odd size, so it is not reversed. The fourth group, 7, 3, 8, 4, has an even size, so it is reversed to 4, 8, 3, 7. After performing these operations, the final linked list becomes 5, 6, 2, 3, 9, 1, 4, 8, 3, 7. Now, let's look at another example. If the input linked list is 1, 1, 0, 6, the groups are 1, 1, 0, and 6. The first group has size 1, which is odd, so it is not reversed. The second group has size 2, which is even, so it is reversed to 0, 1. The third group has size 1, which is odd, so it is not reversed. As a result, the final linked list becomes 1, 0, 1, 6. In a third example, the input linked list is 1, 1, 0, 6, 5. The groups are 1, 1, 0, and 6, 5. The first group has size 1, which is odd, so it is not reversed. The second group has size 2, which is even, so it is reversed to 0, 1. The third group has size 2, which is also even, so it is reversed to 5, 6. After these transformations, the resulting linked list is 1, 0, 1, 5, 6. Finally, the problem comes with several constraints and edge cases. For example, if there is only one node in the list, the output is the same as the input because no groups can be reversed. Similarly, if all groups have odd lengths, no groups are reversed. If all groups have even lengths, every group will be reversed. Additionally, the solution must handle large input sizes efficiently, as the number of nodes can go up to 10 to the power of 5. To solve the problem of reversing nodes in even length groups, we considered several approaches. The first is the brute force approach. The intuition here is straightforward: traverse the linked list one group at a time, measure the size of each group, and reverse the nodes within the group if the length is even. The steps involve identifying groups by traversing the list, counting their lengths, reversing nodes in even length groups, and reconnecting the groups back into the list. However, this approach has significant drawbacks. Its time complexity is n squared, because we repeatedly traverse and reverse groups, and it also uses additional space to store nodes temporarily. Due to these inefficiencies, it is not ideal for large inputs. Next, we considered an optimized in-place approach. Here, the intuition is to reverse nodes directly in the linked list during traversal, avoiding the need for auxiliary storage. This involves initializing a variable for the group size, calculating the actual group length during traversal, and reversing nodes in even length groups in place. This method is more efficient, as it eliminates unnecessary space usage, but requires careful pointer manipulation, which can be tricky to implement correctly. After reversing nodes in an even length group, we move on by incrementing the group size by 1 and repeating the process for subsequent groups. The optimized in-place approach improves performance with a time complexity of O(n), as each node is visited and reversed only once, and it achieves a space complexity of O(1), since no additional storage is used. However, it can be slightly harder to implement correctly due to the intricacies of pointer manipulation. Another approach we considered is a hybrid method that combines pre-computing group lengths with the in-place reversal. In this strategy, we first traverse the list to determine the boundaries and lengths of all groups. Then, during a second traversal, we reverse nodes in even length groups and reconnect them. This method also runs in O(n) time and O(1) space, but the need for two traversals makes it marginally slower than the optimized in-place approach. While it avoids recalculating group lengths during traversal, the additional pass adds a small overhead, making this approach less appealing overall. Ultimately, we chose the optimized in-place approach as the best strategy for this problem. It strikes an ideal balance between efficiency and simplicity. By reversing nodes directly within the linked list, we avoid the need for auxiliary storage and minimize traversal overhead. A key insight is that group sizes increase linearly, meaning the number of groups is proportional to the square root of the total number of nodes. This insight allows us to determine group boundaries and lengths during a single traversal, eliminating the need for extra computations or space. The time complexity of O(n) and space complexity of O(1) make this approach optimal. While it does require mastering pointer manipulation, the implementation becomes straightforward once this is handled. Compared to the brute force approach, it is significantly faster and more memory efficient. Compared to the hybrid method, it avoids the need for an additional traversal, though it is slightly harder to implement. Overall, the in-place approach provides the most balanced solution, offering the best combination of performance and simplicity for this problem. In this problem, we are tasked with reversing the nodes in a linked list, but only within groups that have an even number of nodes. A group is essentially a contiguous subsequence of nodes determined by specific boundaries, such as a special delimiter value or the end of the list. The challenge here is to traverse the list, identify these groups, and reverse only the even-sized ones while leaving the odd-sized groups untouched. To get started, we initialize two pointers, the current pointer to iterate through the list, and the group_start pointer to mark the starting node of the current group. Additionally, we'll use an auxiliary data structure, such as a list or stack, to temporarily store nodes from the current group, which will help us efficiently reverse them later if needed. Now, we begin traversing the linked list using the current pointer. For each node, we check whether it signals the end of a group. This could happen, for example, when we reach a specific delimiter value or the end of the list. Once we reach the end of a group, we calculate the size of the group using the auxiliary list. If the group size is even, we reverse the nodes in the group. If the size is odd, we leave the group as it is. After processing the group, we reset the auxiliary list and update the group_start pointer to the start of the next group. To reverse an even-sized group, we use the stored nodes in the auxiliary list. Once reversed, we reconnect the reversed group back into the linked list by updating the next pointers, first linking the node before the group to the head of the reversed group, and then linking the tail of the reversed group to the node after the group. Finally, we continue this process for all remaining groups in the list until traversal is complete. When implementing this algorithm, we must also handle some edge cases to ensure correctness. For instance, if the linked list is empty, we should immediately return null, as there are no nodes to process. If there's only one group and its size is odd, the list remains unchanged because odd-sized groups are not reversed. Similarly, if all groups in the list have odd sizes, the original list is returned as is since no reversals are needed. The key reason we reverse only even-sized groups is to preserve symmetry. Reversing an odd-sized group would leave the middle node in place, which disrupts the symmetry of the operation. Using an auxiliary list or stack makes it easy to reverse the group by providing access to nodes in reverse order, and careful pointer management ensures the list's integrity. Overall, the algorithm runs in O(n) time complexity because we traverse the list once, and the reversal of nodes within groups is linear with respect to the group sizes. To implement this solution, we rely on specific data structures and traversal techniques. The auxiliary list or stack is used to temporarily store nodes from the current group, which simplifies the reversal process by allowing us to access nodes in reverse order. We also use two pointers, current to iterate through the list, and group_start to mark the beginning of the current group. Imagine the nodes in the list as a sequence, such as 1-2-3-4 or 5-6-7, where the symbolizes a boundary between groups. For the first group, which has 4 nodes, we reverse it to get 4-3-2-1. The second group, with 3 nodes, remains unchanged since its size is odd. After reversing, we ensure the tail of the reversed group connects properly to the next group. The final output in this case would be 4-3-2-1-5-6-7. This demonstrates how we handle traversal, reversal decisions, and reconnections to maintain the list structure. When working with this algorithm, it's important to account for key edge cases. For example, if the list is empty, we return null immediately. For groups with only a single node, no reversal is needed since a single node is trivially symmetrical. If all groups in the list have odd sizes, no changes are made to the list. When the list contains a mix of even and odd groups, we carefully reverse only the even-sized groups while ensuring that the odd groups remain intact. To optimize the algorithm, we can minimize auxiliary storage by using constant space for pointers, avoiding the auxiliary list when the group size is less than or equal to 1. Additionally, efficient management of pointer updates is critical to maintaining the linked list's integrity throughout the process. By focusing on these optimizations, we ensure that the solution is both efficient and robust. Here, we start by defining the solution class and a method called reverse even length groups. Inside this method, we first define a helper function, reverse_sublist, which takes the start node of a sublist and the count of nodes to reverse. The function iterates through the sublist, reversing the pointers of each node, and ultimately returns the new head of the reversed sublist. Next, we create a dummy node pointing to the head of the list, which helps handle edge cases more easily. The variables prev_group_end and current are initialized to manage traversal, with prev_group_end marking the end of the previous group and current pointing to the start of the current group. We also initialize group_size to 1, as the first group will contain only one node. Then, we enter a while loop that runs as long as there are nodes left to process. Inside the loop, group_count is calculated to determine the actual size of the current group by iterating through the list up to group_size nodes or until we reach the end of the list. If the size of the current group is even, we proceed to reverse it. First, we find the start of the next group by moving next_group_start ahead by the number of nodes in the current group. Then, we call the reverse_sublist helper function to reverse the nodes in the current group, and the returned new_group_head becomes the new start of the group. To reconnect the reversed group with the rest of the list, we update the next pointer of prev_group_end to point to new_group_head, and the next pointer of the last node in the reversed group to point to next_group_start. After updating prev_group_end to the last node of the current group, we move current to the start of the next group. If the group size is odd, we simply move both prev_group_end and current forward through the group without reversing any nodes. Finally, we increment group_size to process the next group with one additional node, and the loop continues until all nodes are processed. The method returns dummy.next, which is the head of the modified list. Here, we start by defining the structure of a singly linked list node using the listNode class. This class includes constructors to initialize nodes with or without values, as well as an optional reference to the next node. Next, we define the solution class, where our main method, reverse even length groups, is implemented. Inside this method, we first include a helper function called reverse_sublist. This function is designed to reverse a specific portion of the linked list. It takes the starting node and the count of nodes to reverse as input. Using a for loop, we iteratively update the pointers of the nodes within the sublist to reverse their order. It maintains the current node, the previous node, and the next node during the process, and after completing the loop, it returns the new head of the reversed sublist. After defining the helper function, we initialize a dummy node pointing to the head of the list, which serves as a placeholder to simplify edge cases. We also define pointers like prev_group_end to track the end of the previous group and current to traverse the list. The group size variable starts at 1 and will incrementally grow to determine the size of each group. Using a while loop, we continue processing the list until we reach the end. Within the loop, we first calculate the size of the current group. This is done by iterating through the list with a temporary pointer and counting nodes up to the group size limit. If the group size is even, we prepare to reverse it. To do this, we locate the start of the next group by advancing a pointer group count steps forward. This marks the boundary for the portion of the list we need to reverse. Now, we reverse the current group if its size is even by calling the reverse sublist method. This gives us the new head of the reversed group. We then reconnect the reversed group to the rest of the list by updating the next pointers of prev group end and the current node accordingly. After reconnecting, we move the prev group end pointer to the end of the reversed group, and the current pointer is updated to the start of the next group. If the group size is odd, we skip the reversal and simply move both pointers forward through the group. After processing each group, we increment the group size variable to handle the next group. Finally, once all groups are processed, we return dummy.next, which points to the updated head of the list. To begin solving the problem, we initialize a dummy node with the value 0, which points to the head of our input list. This dummy node helps simplify edge cases during the reversal process. Next, we define pointers. prev_group_end is set to the dummy node, current starts at the head of the list, and group_size is initialized to 1. For the first group, we calculate the group size, which is 1 because it only contains the first node. Since the size of this group is odd, no reversal occurs. We simply update the pointers. prev_group_end moves to the current node, and current advances to the next node. Finally, we increment the group size to 2. Moving to the second group, we again calculate the group size, which is 2 this time, covering nodes 2 and 3. Because the group size is even, we reverse the nodes within the group. Reversing the sequence 2-3 results in 3-2. After updating the necessary pointers, prev_group_end now points to the new tail of the reversed group, and current advances to node 4. We then increment the group size to 3 in preparation for the next group. Now we process the third group, which has a calculated size of 3, encompassing nodes 4, 5, and 6. Since this group has an odd size, we do not perform a reversal. Instead, we simply move the pointers forward. prev_group_end is updated to point to the last node in this group, which is node 6, and current becomes null as there are no more nodes to process. At this point, the modified list is 1, 3, 2, 4, 5, 6. Moving on to another example, let's consider the input 1, 2, 3, 4, 5, 6, 7, 8, 9. As before, we start by initializing the dummy node pointing to the head of the list, setting prev_group_end to the dummy, current to the head, and group_size to 1. The first group once again contains only one node, so no reversal occurs. We move the pointers forward, updating prev_group_end to node 1 and current to node 2, then incrementing the group size to 2. Next, we process the second group, with a calculated size of 2, including nodes 2 and 3. Since the group size is even, we reverse the nodes. The sequence 2-3 becomes 3-2 after the reversal. We then update the pointers accordingly. prev_group_end.next is set to the new head of the reversed group, which is node 3, and current.next points to the next node in the list, node 4. prev_group_end now points to node 2, the tail of the reversed group, and current advances to node 4. The group size is increment to 3. For the third group, which includes nodes 4, 5, and 6, the group size is odd, so no reversal is performed. Instead, we move the pointers forward, updating prev_group_end to node 6 and current to node 7. The group size is increment to 4. Finally, we process the fourth group, which contains the remaining nodes 7, 8, and 9. The group size is 3, and since it is odd, no reversal occurs. We update prev_group_end to node 9, the last node in the list, and current becomes null. The modified list at the end is 1, 3, 2, 4, 5, 6, 7, 8, 9. In a third example, we consider the input 1, 2, 3, 4, 5, 6, 7. Again, we begin by initializing the dummy node, setting prev_group_end to the dummy, current to the head, and group_size to 1. For the first group, which contains only node 1, no reversal occurs. We update prev_group_end to node 1 and move current to node 2, then increment the group size to 2. For the second group, including nodes 2 and 3, the group size is 2, so we reverse the group. The sequence 2-3 is reversed to 3-2. After updating the pointers, prev_group_n.next points to node 3, current.next links to node 4, and prev_group_end is updated to node 2. Current advances to node 4, and the group size is increment to 3. The third group, consisting of nodes 4, 5, and 6, has a group size of 3. Since the size is odd, no reversal is performed. We move the pointers forward, setting prev_group_n to node 6 and advancing current to node 7. The group size is increment to 4. Finally, we address the remaining node, which is node 7. As it is a single node, no reversal is needed. The pointers remain as they are, and we reach the end of the list. The final output for this example is 1, 3, 2, 4, 5, 6, 7. This concludes the solution walkthrough for all three examples, demonstrating how the algorithm handles groups of varying sizes and performs conditional reversals based on group length. To analyze the time complexity, let's break it down step by step. First, the outer while loop is responsible for traversing the entire linked list. Since the current pointer visits each node exactly once, and there are n nodes in total, this loop runs n times. Next, for the inner while loop, we determine the size of each group. The group sizes follow the pattern 1, 2, 3, and so on, until all nodes are grouped. Since every node belongs to exactly one group, the total work done by this loop is proportional to n. Finally, for even length groups, we reverse the nodes. Reversing a group of size m takes m time, and since each node is reversed at most once, the total cost of all reversals is also proportional to n. Now, let's consider the operations involved in connecting groups back into the list. For each node, these operations are simple pointer manipulations, which take constant time, or O1. When we combine all these steps, traversing, reversing, and connecting, the total work done is proportional to the total number of nodes, n. Therefore, the overall time complexity of the algorithm is O(n). For the space complexity, the reverse_sublist helper function uses a few pointers, such as previous, cur, and next_node, to reverse nodes. These require only constant additional space, or O1. Since the implementation does not use recursion, there's no extra stack space required, and the dummy node used for convenience is also a constant space addition. Thus, the space complexity is also O1. In summary, the total space complexity is O1, because the algorithm operates entirely in place without any additional data structures. Now let's analyze the algorithm across different scenarios. In the best case, when the linked list is very small, the algorithm still processes each node exactly once, leading to a time complexity of O(n). For the average case, with a typical input of length n containing a mix of even and odd-sized groups, the algorithm again performs O(n) work. Finally, in the worst-case scenario, where most groups are even-sized and require repeated reversals, the algorithm still processes each node only once. This means the time complexity remains O(n), even in the worst case. To understand the efficiency of this approach, let's compare it to a brute force method. A naive solution might involve extracting groups into separate data structures, like arrays, reversing them if they're even-sized, and then reconstructing the linked list. This would require additional space to store the groups, leading to an O(n) space complexity. On top of that, the overhead of reconstructing the linked list would make the brute force approach less efficient overall. In contrast, the optimized solution avoids any extra space for group extraction. By directly manipulating the linked list in place, it reduces the space complexity to O1 while maintaining the O(n) time complexity. This makes the current implementation significantly more efficient. Finally, let's validate the time complexity mathematically. The total number of iterations across all loops is proportional to the number of nodes, n, since each node is processed exactly once. Each operation, whether it's a traversal, reversal, or connection, is constant time per node. This means the total work done scales linearly with the number of nodes, confirming the time complexity is O(n). For space complexity, the algorithm uses only a few pointers without allocating additional memory, which ensures constant space usage, or O1. In conclusion, both the time and space complexities of this algorithm are optimal, making it highly efficient for the problem at hand. One common mistake to watch out for is incorrect handling of edge cases. For instance, if the linked list is empty or contains only a single node, failing to validate the input beforehand can result in null pointer exceptions or invalid outputs. Always ensure your code accounts for these scenarios before diving into the main logic. Another frequent issue is not resetting pointers after processing each group. When reversing groups in a linked list, it's critical to reconnect the previous group's tail to the current group's head. Forgetting to update the traversal pointer after processing a group can lead to broken links or even infinite loops. Additionally, reversing sublists in place requires extra care. Every node's next pointer must be updated correctly, as missing even one can break the overall structure of the list. Lastly, inefficient traversal is something to avoid. For example, if you're traversing the list multiple times, once to count nodes and then again to reverse, it can unnecessarily increase runtime complexity. Instead, aim to minimize redundant iterations by thoughtfully combining steps where possible. Using extra space without justification is another pitfall to be mindful of. While auxiliary data structures like arrays or stacks can simplify the logic, they introduce additional space overhead. If the problem specifies in-place reversal, avoid extra space unless explicitly allowed. Now, let's consider some interview insights. First, pattern recognition is key. Linked list problems often revolve around pointer manipulation, so practicing fundamental tasks like reversing lists, detecting cycles, and splitting or merging lists can strengthen your understanding. It's also essential to prioritize edge cases. Interviewers commonly test scenarios like empty lists, single-node lists, or lists with odd and even lengths. Mentioning these during your explanation demonstrates thoroughness. Furthermore, be aware of trade-offs between iterative and recursive approaches. While recursion can feel more intuitive, it may lead to stack overflow issues for very long lists. Finally, optimization is critical. If your initial solution is brute force, be prepared to discuss ways to reduce redundant operations or improve space efficiency as part of your thought process. Several related problems can help solidify your understanding of reversing linked lists. First, the reverse linked list problem, LeetCode 206, is an essential building block for reversing sublists or groups. Mastering this problem lays the groundwork for more complex variations. Next is reverse nodes in K group, LeetCode 25, a more advanced challenge where nodes are reversed in groups of K. This problem requires careful handling of group boundaries and pointer updates, making it an excellent practice for group-based reversals. Another useful variation is swap nodes in pairs, LeetCode 24. Here, instead of reversing groups, nodes are swapped in pairs, which simplifies the logic but still provides practice in managing pointers effectively. Lastly, the palindrome linked list problem, LeetCode 234, involves reversing part of the linked list to check for symmetry. This makes it conceptually similar to group reversal and a valuable addition to your preparation. When solving problems like this, it's important to understand the alternative approaches and their trade-offs. An iterative in-place reversal is highly efficient in terms of space, using only 1 extra memory. However, it can be error-prone, as it requires meticulous bookkeeping of the previous, current, and next pointers to maintain the list structure. On the other hand, recursive reversal is often more elegant and intuitive, but it comes with the downside of additional stack space usage, which could lead to stack overflow for very large lists. Another option involves using an auxiliary data structure, such as an array. This approach simplifies the reversal process by offloading the nodes to an external container, but it adds an space requirement. It's a good choice when space constraints are lenient. Lastly, a double traversal approach can be used. In this method, the list is traversed once to identify group boundaries, such as odd or even lengths, and then a second time to reverse the groups. While this can make the implementation easier, it can lead to increased runtime complexity, potentially reaching n squared in certain cases. Each approach has its strengths and weaknesses, so it's important to choose based on the problem constraints and requirements. Great job following along. To recap, we tackled the problem by reversing nodes in even length groups. Mastering such linked list problems is essential for interviews and developing a deeper understanding of data structures. Thanks for watching, and don't forget to like, subscribe, and watch more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!